Use a computer to symbolically compute d dt partial dl dq dot j minus dl dqj equals qj. Use a computer. Okay, so that's the motivation. I'll start from the very basics. We've looked at symbolic derivatives some time back. I think we talked about symbolic derivatives in context of Jacobians. When we would try to compute the Jacobian, I showed you how to do it by using a symbolic package. So example is, if you want to, I'm just going to compare how you would write a code to compute a very simple derivative, say derivative of f0. Let's say f0 is the equation I need to compute the derivative of. It's x squared plus 2x plus 1. If you do it by hand, use just do df dx, be 2x plus 2. And then if you want to compute df dx at some point x equals, let's say 1, you will write it maybe like this, then that's equal to 2 times 1 plus 2, which is 4. Okay, so that's pretty simple, right? How would you do this with Python? Well, you will first import SymPy, which is the package which does symbolic calculation, as sy. You can call this any name. Then you'll define symbolic variables. This is very important because how would Python know that x is not numerical value, it's a symbolic value? Well, you need to say x equals sy dot sim by x, and then you got to say real equals true. Okay, I learned this the hard way. Once when I did calculations using symbolic without defining real equals true, I started seeing answers which were complex, and I realized that I should have defined x as real. Then you define the variable f, which will be x Okay, I don't know if you know this, but you cannot define x raised to 2 in Python. You can define that in MATLAB. To define x raised to a power, you need to do the multiplication 2 times, or the asterisk 2 times, plus 2 asterisk x plus 1. And that basically defines f. And then if you want to compute df0 dx, that's simply use the diff function in the symbolic package. Just go f0x, it will find the derivative. And then if you want to evaluate the value of df dx, all you do is you say df0 dx dot subs, and then you tell you what variable, which is in this case x, and its value, so 1, and that will do the needful. It will give you the same answer as the one you got using hand calculation. Okay. Okay, so this is numeric hand calculation. This is Python. Let's call that Python symbolic. It turns out that you do not need the symbolic package to compute the derivative, right? You don't really need the analytical formula. The analytical formula is this one. if you have the analytical formula, it's super easy to compute the value, right? You define that as a function, you put a value of x equal to whatever you want, and it will give you the value. But what if you are only given this, which is the function f, and you're told to find the derivative of f, but you don't want to use the symbolic package? Well, it turns out there's something called a numerical derivative, which doesn't require you to use the symbolic toolbox. And that's useful in some scenarios where, um, in this case, you kind of stuck for this equation, you kind of stuck doing the symbolic calculation because of the way it's set up. But sometimes you may just want to find the derivative for other things. Like, for example, when you're doing optimization, you need the derivative and you don't want to do it symbolically. Also, sometimes, closed form solutions like this may not be available. You just don't have it. F0 might come as a result of a very complex calculation. So it's a code which gives you the result F0. It might be some ODE integration, right? In this case, a closed form solution is not available. How do you compute derivative that way? The answer is through numerical means. So here is using Python, but using numerical derivatives is another way of computing the derivative. So Python numerical derivative. So key idea here is if you have the function f0, and then you're trying to estimate its derivative at some point x0. Here x0 I think was 1. What you do here is you find the value of f0 at a neighborhood, let's say x1 close to x0. And then if you know the value at x1, then you can compute tx as f of x1 minus f of x0. So f0 is that function, right? f0 x1 minus f0 x0 divided by x1 minus x0. What is x1 here? This is something which you choose. So typically people will add a small perturbation. Okay. This sometimes is also written as 1e negative 4, the same as 1e negative 4. So it's a small perturbation. And why is this true? Well, it's because if you know the definition of the derivative, it's basically the value of df dx is f of x minus f of x1 minus f of x0 divided by dt or delta t or delta x, or in this case where delta x tends to 0. The smaller the value of delta x, here delta x being 1e negative 4, the more accurate it is. Now, you can't make it arbitrarily small. You can't make it 1e negative 20 or 1e negative 30. That wouldn't make sense because your computer has a certain precision. It can only go up to, I think, 13 decimal places. So if you do 10 raised to negative 20, it won't really register it because it doesn't have 20 decimal places available. It only has 13 decimal places. So the thumb rule usually is that if your machine accuracy is 1e negative 12 or 1e negative 13, you always use the square root of that. So 1e negative 6 is actually a good value to beat that truncation error, which comes because of limited accuracy. It turns out that this derivative is this method is called forward difference, and it's actually quite accurate. But if you want to improve it further, there's a better method. It's called central difference. In central difference, what you do is you take f, and there's a point of interest, but then you find 2 points, one before x0, so that will be x2, and then one after x0. So x1, x2 are close to x0. This is the function f0. And then the derivative is defined by a central difference formula, which is df0 dx equals f0 x2 minus f0 x1 divided by x2 minus x1. Okay, you can use the same. Uh, you can use the same. Well, you can use the same kind of formula for x1, x2. x1 equals x0 plus 1e negative 4. x2 equals x0 minus 1e negative 4. This is known as the central difference formula. And it is more accurate than forward difference for the same step size. The step size here is the value 1e negative 4. So the same step size you see, it's actually almost twice as accurate as power difference. So you want to use that. Okay, and I think we'll be using it some point of time, not immediately. See, so before I go to the next one, which is the chain rule and how to do chain rule using symbolic calculations, let me just show you some code which does exactly what I said. There are, as I said, the three ways to do it: hand calculation, which is easy to do, you learned it before; symbolic toolbox; and then use the numerical derivative, which is here. So here is, let's see, I need to open, okay, Visual Studio Code. Okay, so we have symbolic, let's open this. Okay, so let's go to the symbolic one. This is exactly the code I wrote down there, right? Import a symbolic toolbox, define x as symbolic variable, define f0. This is just printing it, not very important here. Find the derivative as diff f0x, and then I just print it out. Then I try to find the value of df dx at x equals 1. That is just the subs with x val equals 1. Let's run this. And the answer should be what, 4, right? It's still running. Yeah, so it basically told you what f of x is, what df dx is, and then the value is 4. I did the same thing using the numeric package. Now, I did use symbolic sympy just because I wanted to define f of x and keep it to show you what it is. But when I actually do it here, I really don't need the symbolic toolbox. Okay. So x val equals 1. I took a perturbation 1e negative 5 instead of negative 4. F0 is the value at x val. F1 was minus. F2 is with x val plus perturbation. So the forward difference is F2 minus F0. So I interchange the F1 and F2 in here in the code. It is different in the notes. F1 and F2 are interchanged. So F2 minus F0 divided by perturbation, because F2 happens to be the value plus, so it's plus perturbation. If you want to do F1, or you want to do F1 instead of F2, it will be F0 minus F1. It's called backward difference. It's have the same accuracy as forward difference. And then central difference is F2 minus F0 divided by 2. I actually did a mistake here. This should be twice perturbation, my bad. I should fix that in the code. I'll just fix it, but it's twice perturbation. So let's run this. And then you'll see that here, f of x forward difference, it gives this value, central difference. Now, if you see the forward difference, you'll see that there is a 1 sitting in 1, 2, 3, 4, 5, sixth place. That's inaccurate, actually, right? Now, you don't care about the 1 in the sixth decimal place. But if you are computing something like the distance to the moon or something like that, then that 1 would actually be matter, because we care about distance in miles, and that might be 10 times 10 raised to 6, right? So you'd be off by whatever, or maybe a mile or two. And so if you want to land a rover, then you're going to be a mile away, right? So it matters in some cases, it doesn't matter in some other cases. But central difference is actually pretty good. It actually gave you 0, 0, 0 all the way, and it's actually incorrect over here. Well, this one is 6 decimal. That one was almost, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, almost 12 decimal places, just to show you the difference. Okay, I need to fix that. Let's move on to chain rule. Uh, but before that, let me fix this in my code. So the thing I need to fix here is that this should be, oh, this is right, my bad. This is absolutely fine. This will actually come out to be 2e negative 4 if you check it, right? So it's fine. Yeah, so it's not incorrect. Okay. Okay, let's get to the main thing which we're interested in, which is if you look at this calculation, it's much more than that. You have a partial derivative there, and then there's a complete derivative. So what we need to understand is chain rule. So this will be a review of chain rule first, and then I'll show you how to implement chain rule using symbolic toolbox. It's not a big change, but I think we'll go slowly. So it's kind of important because deriving the equations correctly relies on knowing how to do this. So chain rule, okay, here is how I learned it. If you have f of x of t, f1 x of t, and then you are told to compute df1 dt. Okay, so normally when you take, if you do f1 with respect to x, that would be the derivative we talked about earlier. F is just a function of x and you can compute the derivative. But here, f is a function of x and x is a function of t. And the way I like to, or at least I learned this as a freshman, was f1 is a function of x, is a function of t. And what you're trying to do here is you're trying to compute the derivative of f1 with respect to t. And so what you need to do is, if you want to go to t, you need to go via x. So you need to go first through x and then to t. So what you do here is to compute df1 dt, you first go from f1 to x. So that would be df1 to dx, and then go from x to t. So that is the chain rule. Right? The x appears here because f is a function of x, x is a function of t. So you follow the blue arrows, and that's what I wrote down. This is the chain rule. Okay, example. If I told you that f1 is sine of x of t, then you do df1 dt is df1 dx dt. So when you're doing the first part, which is this, you treat f1 as is just sine of x. Okay, so when you treat f1 as just sine of x, you take the derivative of sine of x with respect to x, the first part. So I'll write it like this: sine of x dx, and then dx dt. So the first part will just be cosine of x. And I would write the t because x is a function of t, and then dx dt, you can keep it as it is, or if you're given the value of dx dt, then you'll put it there. Okay, so that's how you would use the chain rule. Okay, now let's make it a little bit more harder. I'm going to introduce two variables for the function f1. Instead of one variable x, we'll have two variables because eventually our Lagrangian will be a function of more than one variable. F will be L eventually. Okay, so let's see how to do this for two variables. Yes, if f2 is a function of t and the derivative of t, then compute df2 dt. So you can think of x of t as the position. You can think of x dot t as the velocity. And then the Lagrangian, which is what we are shooting for, is actually a function of position because you'll have the gravity mgy, and then it'll be function of velocity because there will be half mv square. Okay, so let's see how to do this. Now, I use the same trick. We have f2, it's a function of x and x dot, and that's a function of t. So in order to compute uh, df2 dt, I need to do the following two things. I need to go from f2 to x, and then from x to t. And the other thing I need to do is I need to go from f2 to x dot, and then x dot to t. Right? The blue one is what we've done before for one variable, but the green arrows is what we need to also do in order to find the derivative because it's a function of two variables. So we'll apply the chain rule now. We have df2 dt. So I trace the blue arrows. So if I trace the blue arrows, I need to go df dx dx dt, chain rule. But then I need to also go through the green arrows. So I need to go from, this should be f2. So that would be df2 dx dot, okay, dx dot dt. So don't be worried about dx dot appearing in the denominator. Treat x dot as just another number or variable like y, right? You just put it there. So that's the chain rule for you in 2 dimensions. And it's clear that you can extend this to multiple dimensions. You can have x dot, you could have y dot also. So x dot, y dot, that's what we'll get to. You could have, and then the chain rule will have 4 numbers, right? We'll have x dot, y dot. Okay, so let's see an example of how to do this. So f2 is, let's say, x of t and x dot of t. Okay, so product of the position and velocity. If you want to compute df2 with respect to dt, we'll go with df2 dx dx dt, the first part. And the second part of the chain rule, okay, should have written it blue. So df2 dx dx dt, then df2 dx dot dt. Okay, so for the first part, when I take the derivative of x times x dot with respect to x, I treat x dot as a constant. So the first part would just be, you know what, let me write it down, that way it's super clear. X times x dot dx dt plus x times x dot dx dot dt. Yes, so the first part, when you take the derivative, this should be dx. So this and this. Okay, for the first part, when I take the derivative of x times x dot with respect to x, x is a constant, x dot is a constant, and x is a variable. So the first part, you'll have pretty much dx with respect to dx, which is going to be 1, and x dot stay that as it is. And then x dot, this thing is just x dot all over again, plus the second one, I treat x as a constant, and I take the derivative of x dot, so that'll be just x. And then dx dot dt, it's basically the derivative of velocity. It's going to be acceleration. So my answer is df2 dt is x dot square plus x times x double dot. Okay, so let me show you numeric code which does the second example. I think I have set it up. So this is using the symbolic toolbox. Okay, so I'm going to show you the second example, or maybe I have both examples here. Yeah, my bad. I have both f1 sine of x, and then I also have f2 x times x dot. Now, what I did here is use the symbolic toolbox. So I need to create three variables because eventually I end up with x double dot, right? So I have x dot, x double dot with a position, velocity, acceleration. I create them as symbolic variables. Say real is true. The first example was computing derivative of sine of x. Now, if you write a sine of x and take the derivative with respect to t, you have to remember you need to use chain rule. So this part is df dx, right? df dx, and then this x dot. So then that's just print that. And then when you take f2 is x times x dot, it's the chain rule is right here. It's basically doing df dx x dot plus df dx dot x double dot. Okay, so when you run this, for df d1, we had computed x dot times cosine, I think. Yeah. And then the second one was x dot x double dot x dot. This just got switched. This was the first expression of the second one. Okay. Now the thing is, there's no inbuilt value to do chain rule. Symbolic toolbox is not smart enough to figure out chain rule, but you will have to write it down the chain rule yourself, right, using diff. Okay. So the Euler-Lagrange equations look like this. Right now, what we have seen for the projectile is that the Lagrangian is half m x dot square plus y dot square minus mgy. Okay, so what we have done in the past is we've noticed that the qj, which is the degrees of freedom, are x and y, and then qj was the force, right? f dx, f dy. Anyway, qj is something which is not of interest to us here because it's basically the right hand side. We don't really need to take derivative, but we need to find the left hand side, take the derivatives. So what we notice here is that how this is connected with chain rule is that the Lagrangian is actually a function of x, y, x dot, y dot. Now it's not a function of x. Okay, I just write it for in that fashion just to make it more generic. So we have L is a function of x, y, x dot, y dot, and t. Okay, and then for this equation, okay, so for this equation, we know that we need to take qj equals x, qj equals y. So how, let's see what happens when you do that. So if you take qj equals x, then we have d dt of dl dx dot minus dl dx equals f dx. So we have to do the following. We need to compute this part. We need to compute this part. That's a derivative. It can be done using the symbolic package. For this part, we just need to use diff, right? All we need to do is lx. There's no chain rule involved. So there's no chain rule because L is a function of these variables, and we're just trying to compute the derivative with respect to one of those variables, right? It's not trying to compute derivative with respect to t. When we try to do dl dx, it's just diff, it should be x dot. Diff L x, no chain rule. However, when we try to compute d dt of dl dx dot, it is this part, this is where we need to use chain rule. Now L dl dx is going to be a function of, so let's call this Lx dot, no chain rule. In order to compute this, we need to do dlx dot dx dx dt. Remember L x dot, L is a function of all this, but Lx dot could also be a function of all this. So I need to do this actually 4 times, right? There'll be 4 things coming up here. dl x dot dy dy dt plus dl x dot dx dot dx dot dt plus dl x dot dy dot dy dot dt. There are 4 terms. Okay, some of them will clearly be 0, some of them won't, but this is the chain rule. There are 4 terms because there are 4 things here, and those 4 things will show up like this. So every time we have to do this, we'll invariably see that we'll have, if there are 4 variables, x, y, x dot, you'll have to do chain rule, but it'll be 4 terms. If that L had like 8 terms, you'll see 8 terms in the chain rule. Now, clearly, something like this is going to be very time consuming to do by hand, and that's why we want to use the symbolic toolbox to do it. So I'm going to show you a code which does the same thing, chain rule, for the Euler-Lagrange for the projectile, and I'll stop. So here is some code I wrote. Okay, so import sympy as sy. I have variables x, y, x dot, y dot, x double dot, y dot. I also need to define mass, gravity, and the drag force. So position, I'm just going through the steps 1 to 3, which we had for the Euler-Lagrange. Position velocity, we don't need to do much because it's already defined. I compute the kinetic energy, potential energy, compute Lagrangian L. This is just getting the drag force. Now I have 2 ways I wrote the equations of motion. I did this manually. So dl dx is diff, as I said, there's no chain rule. But when you do d dt, you need to do chain rule, and that will have 4 terms. Okay, and then dl dx, and that's EOM1. EOM2 will have with y, and those are 2 equations. You'll have 2 equations because there's motion in the x direction and motion in the y direction. So this is method 1, where I explicitly write each term down just like I have a formula. But I also do this in a more automated way. If you define q, q dot, q double dot, then this code here runs a for loop and sort of does that chain rule with whatever number of times it needs to do, because you've stored them in q dot. So this is like a way of automating the same code so that you don't have to individually write like 8 terms. If you had like 20 terms with q dot, this code will actually take care of it. So I commented out this code. I'll run the first part, and then you just need to uncomment the second part and run it in order to automate it. So this is, I'm almost done. It's 10:50. It's basically gave me the equations, x double dot, y double dot. You can check it against the equations I derived earlier.